In some cases, the hosts in the NTP network are not set up for polling. Instead, the time servers are set to broadcast, and they will broadcast at some time frequency, and all the clients need to do is just to listen for the broadcasted time. Overall, the goals for NTP is to enable clients across the internet, or maybe even on a local real-time network, to be accurately synchronized to a UTC, despite message delays. To make this work, statistical techniques are used to filter data and gauge the quality of results. NTP also provides a reliable service. It can survive lengthy losses of connectivity, and it provides for the use of redundant paths and redundant servers. NTP is also scalable. This allows clients to synchronize frequently and to offset the effects of clock drift. As we know, every clock drifts over time. It also, in certain versions, provides protection against outside interference by allowing the use of authentication. So as we mentioned earlier, NTP servers are arranged in a strata. So here we have stratum 0, stratum 1, stratum 2, and stratum 3. Stratum 0 machines are connected directly to an accurate time source. Stratum 1 machines are synchronized from stratum 0 machines, and the stratum 2 machines are synchronized from stratum 1 machines, and so on and so forth. And NTP version 4 has different types of synchronization modes. It has a multicast mode for high-speed LANs that is lower in accuracy but is more efficient. It has a procedure call mode similar to Christian's algorithm. We're going to look at Christian's algorithm later on in this lecture. And then it has the symmetric mode. Symmetric mode is intended for master servers, where you have A probes B and then B probes A. And A adjusts clock only if A stratum is greater than B's. Also, peer servers can synchronize with each other. So you're talking about servers on the same stratum can synchronize each other, provide a mutual backup. And the pair of servers can retain data to improve synchronization over time. So there's a lot of different ways that NTP can be tweaked and configured to make the network, make time on the network as accurate as possible. There are things that NTP is concerned about as far as clock quality, such as precision, which is the smallest increase of time that can be read from the clock. So the greatest precision is usually found on the time sources in stratum 0, and different devices on the network will have different precision capabilities. And you usually want the more precise devices at the lower numbers or at higher in the stratum. Jitter is the difference in successive measurements, obviously on a network that where you're going to have inconsistencies in time due to network traffic. You can experience jitter, which is the difference in successive measurements. And this can be due to delays on the network. It could be due to delays on the operating system of the sender or the receiver, because they're doing more than just dealing with time, they're doing other processing. And wander, in case you have a clock whose oscillators become unstable. And then accuracy. And this is the thing that you're always going to be working on, is how close is the clock to UTC. Let's talk a little bit about NTP messages. And unfortunately, I don't have a Wireshark lab, but I may be able to find a video that we can add to the additional material to show you some NTP messages across Wireshark. So NTP messages have a procedure call and a symmetric mode, and messages are exchanged in pairs with a request message and a response message. Time is encoded as a 64-bit value, and then NTP calculates an offset for each pair of messages. There is an estimate of time offset between the two clocks, and there's also the travel time, which is half of the total delay minus remote processing time. This is what we also refer to as jitter or dispersion. There is a maximum offset error, and this data, the maximum offset error, this should be to the right here, is used to find the preferred server. You basically probe multiple servers, each of them several times, and you pick the lowest total dispersion and lowest stratum. The message structure also has a leap second indicator, a version number, the type of mode, the stratum, the polling interval, and the precision of the local clock. That's very important because in polling you can use this information to pick the most precise clock. Other information needed to do all your calculations includes your route delay, which is your total round-trip delay to your primary source, your route dispersion, which is your nominal error relative to the primary source, the ID of the reference clock that you're going to use, and also for calculation purposes, a reference timestamp, and authentication with a key ID and a message digest, and a digital signature, which is ignored in the simple NTP. The message structure will have a T1, which is the originating timestamp, which is the time request, the time of the request departed the client. A time 2, the received timestamp, which is the time the request arrived at the server. And time 3, the transmit timestamp, the time the request left the server. SNMT, or Simple Network Time Protocol, is a subset of NTP based on the unicast mode of NTP. It can operate in multicast or procedure call mode, and it's used where the server is the root node and the client is a leaf of a synchronization subnet. In SNMTP, the route delay, route dispersion, and the reference timestamp is ignored. But SNMTP is a good good way to take a look at a simple example of how the clocks synchronize with each other. So imagine you have a server and a client. At time T1, a request for time is sent from the client to the server and arrives at time T2. It takes the server from T2 to T3 to respond to the request, and then it can send its reply, which is received at the client at time T4. This will result in a round-trip delay of T4 minus T1 minus T2 minus T3, and a time offset of T2 minus T1 plus T3 minus T4. So let's take a look at an actual example. So imagine, I apologize if I get to change this back from superscript to regular font. But imagine, no, yeah, a little later. All right, let's do this really quick. Imagine that you have on the client, they're obviously set at different times. They're a little bit off from each other. You have time T1 on the client set to 1100, so it's way off compared to the server. The server has time T200, and it takes 50 time units before it responds, and so at time T3 of 850 it responds, and it's received at the client at its time 1200. So based on what we talked about before, our offset is time 2 minus time 1 plus time T3 minus T4, and you take all of that and you divide that by 2. So you do all the math and you have an offset of 325. So now you basically take your final time and you subtract from it your offset, and now you have a time of 875, and based on our knowledge of how long this takes, that 875 at time T4 should correspond to the time 875 on the server. In Christian's algorithm, we just take the time T4 and the time T5 of the client, we divide it by 2, we take time TS, which is halfway between T2 and T3, and then we add that to the offset, and we get 875, which is also the same time that we have over here.